Okay, so these lines I drew here, these white lines, they are all starting from this 90-degree line here. And you'll notice that they are all headed towards the equator. And believe it or not, these lines are all directly east. And that's the problem that people don't get. So when they say, well, the sun is rising south of east, well, yeah, imagine that you're down here. And of course, the sun is going to rise south of east because this is east. So, we've all been taught, or we think that when you look east, that you're looking along one of these lines here, but you're not. And if you just turn like this and see that, let me spin this thing here, and you get down, come on, there we go. So if you get down here and then we look like, and you can actually go to the actual date of the equinox. So if we're here, just getting down this line here and there, so we're facing directly east there. And then if you pull up your date and go back to the 21st, you'll see that the sun rises directly right over that line. But the problem is that people think that line is not where it is, but you're actually looking to the equator. So you'll see here on the 21st, where's the sun? So the sun rises right there on that line on the 21st. But then it does every line, all these lines that if we go and find the next one, well, that's Tropic Capricorn. But when you find the next line there, that's why it gets confusing for people. So we see here as well, get down here, and you'll see that it rises there as well. So what we're getting is everybody's looking to the equator. And that's the problem that people don't understand. They think that, they think that you're looking east, which we would assume is along this line here, right? So if we start here, you would think east is on this line, but this line tails off this way. This actually goes this way. And the crazy thing is, if you look at these lines, these white lines here, and then if I turn these three on here, so those lines are west. So, this is kind of the issue, is that yes, if you're standing at this location right here and you're looking dead east, well, if you turn around, you're looking dead west. So to us, we think that it would look like a cross when you get far away from it. But if you really pull back, you'll see that line is actually, and it's always a great circle. That's where these lines come from. They're all great circles, but it's certainly peculiar. It's not the way you would think. It is kind of counterintuitive. But people think that, I know the big joke about the flat earth model is that if you circumnavigate the flat earth, that you're always turning your wheel. They'll just laugh at you and say, well, what do you mean you would always be turning the wheel of your boat or of your plane? Well, it's the same thing on the globe. People think that if you started out this way, that you would, well, if you stayed straight, you would stay on this white line, and that you would go nowhere near where you think you're going. People think that if you go on this line, that's a straight line. No, you'd be turning left. You'd always be turning left, because no matter where you're at, take each of these crosses, east is this way, and then east is this way, and it constantly adjusts. If you just stayed east from your heading from where you started, you would coast down in part of the Great Circle, and you'd end up here like at this equator here. And then also, if you bring up like a spherical triangle, this is just another thing that they always use, right? So here's your triangle. They always talk about how the globe has a spherical triangle, meaning if you pull in here and you look, there's the 90-degree angle, and then you pull back, there's a 90-degree angle over here, these green lines. So you'll see again that that's a 90-degree angle at this green line. And so you have 90, 90, 90. So you've got your 270 triangle, which we know doesn't exist on a regular flat map, but that's the way they get away with it, because these lines are nowhere near parallel. They both curve in. And again,
right, it's an oblate triangle, and so obviously the angles are going to meet. It's not as if we're dealing with straight lines.
Right, because of course that'd be impossible, right? If you did three 90-degree angles, or one here and one here, you would just end up with a unfinished box that would never connect. And that would be the definition of it, that if you have a 90-degree angle here and a 90-degree angle here, well, these lines can never meet. They would have to remain parallel to each other for forever. But because of the way the globe works, that they're angled down, and that's the thing about the flat earth that I think people don't understand, that it works the exact same way. It just so happens that if we drew these 3 points on a flat earth map, that they just wouldn't make a spherical triangle, they would just make a regular triangle. And people would say, oh, but you're not making a 90-degree turn. Well, neither are these people here. Well, they technically, I guess you can. It depends how far you're talking about. Are you talking about If this person came down here and made a 90-degree turn and went this way, sure, you made a 90-degree angle here, but you're actually walking back towards this angle here. You're not staying at that 90-degree angle, or else you'd be following this white line here. So it's just something that people don't understand. They think that when they say the sun rises to the east on the equinox for everybody, you know, and I can admit I was one too that thought that meant east for everybody. But if everybody's east is technically looking at the equator, then it makes tons of sense to me. Of course, that on the equator, sorry, on the equinox, the sun is above the equator. And if everybody's 90 degrees is looking at the equator, then of course the sun rises in the east for everyone. So, you know, it's just one of those things. It's the same thing that they have a problem with they keep going on and on about things rising south of east down in Australia or wherever. But again, if you were here, well, let's say we're at this line here, and you're wondering where the sun rises on, say, somewhere near their summer down here in the south, well, it's going to rise south of east. And it doesn't mean, you know, they're looking at it as this is east, this line that kind of tails off this way. So there's, you know, lots to do with this, with the globe, and the whole idea of it being a deception, that it's not, you know, we don't live on a globe. And just because they were able to put longitude and latitudes and give us our coordinates on the idea of a globe doesn't mean that's where you live. So that's,
well, you know, the whole argument that you mentioned about if it, you know, on a flat earth, you would have to, if you're going west, you would have to keep turning your car to the right, or your nose of the plane to the right, or whatever. I mean, we're dealing with such vast distances that it would be just minor course corrections anyway. But from what I gather, if you align your car to a really, really distant, say, cityscape that you can see that's 30 or 40 miles off in the distance, where you can sort of freely travel, and align it to where it's, say, like due west or due east of you, that it will start to slightly phase out of that alignment, which is sort of, you know, helpful, or it sort of aligns with the azimuthal equidistant sort of flat earth map. But we're not talking about, you know, major course corrections where you're constantly turning right to go west or east. It's just very slight course corrections over long distances to where, you know, you wouldn't even notice it. And in fact, you know, as you're showing here, even such course corrections are necessary, assuming a ball. So, you know, it's Absolutely. A moot point either way.
It's exactly the same both ways. That's kind of the whole point of it, is that, yeah, if you just set out and you're just going directly east, then you're right. You would never even notice that you're making that kind of a turn. And that's part of the deception, is that people think, again, if you get down in here, that east is actually this white line here. So if you notice, and this is going across several states, or at least a state or two, but you notice that it just looks the exact same as this green line. As we head off this way, you'll even notice here, they look identical. So we've gone 5 or 6 states all the way to off to the coast, the East Coast. And we don't look like we've changed at all. But, you know, as you start going further, oops, that's the wrong white line. My bad. This white line up above here. So you'll see here, this white line and this green one are staying together. But then right here, they start to widen. And then you'll see that this would have been going. And Bob, you would know better because you fly. So that green line is what they call a heading, right? And then the white line would be like what they call a track. Is that the right names, or is there a different name for that?
No, that's actually very aptly named. Yes.
Okay. Yeah. So I mean, you know, when you put in your heading, it's like, you know, you're heading this direction, you're heading east, and the plane, you know, usually you do that through an autopilot, that it would keep on this track. And then if you are tracking a certain, and that's usually if you see a plane and it says it's going, you know, in this case it would be going, you know, 90 degrees or 89. That's you're tracking that that direction. But heading and track are quite different, because we just explained it. So anyway, it's
right.
just
Your heading is your heading is just basically your azimuth bearing, and of course that is corrected from the compass and also the magnetic declination, and then that's what you set your azimuth to on your plane, and then that's what you fly your heading from. So yeah, very good.
And I'll show this one more time just because I think it's important to know. But if we were up here in Denver where Bob is, and we track 90 degrees this way, so I'm going to put it at exactly 90. Okay, so right there. So that's 90 degrees. And if you were to take that spot that you went to and you were to track backwards west, that you would think that you go back where you came from. That would be pretty much what I would think everybody would agree with. But actually, if you grab that spot here, we'll make sure we get right on it, and you track back west, and so we're going to go to 270. 270, which you'd think would be right on this red line, is actually right there. Oh, that's 270.2 right there, 270 exactly. So that's what people need to understand, is that if this is dead east from this location, then you would think that this would be dead west from this location, but it's not.
That would make way too much sense.
Right. Yeah, that would be like reality or something. But no, this is kind of part of the deception that people need to see and explore and research, because in this lies the entire lie. The entire deception is inside of this globe, and we can pick it apart and we can kind of figure out how they constructed the globe. And obviously that's why the Masonic symbology is the square and compass and the G and geometry, and it's all in their ability to trick you into thinking that you live on a ball, that you are stuck here, that there's no possibility of anything else. And that's how we were taught. So I can't hold it against anybody. I was taught the same way. But when you realize that at a certain point, you realize, well, we weren't given the truth, that we were given a story that explains what they wanted to explain, but isn't the truth. Well, then you need to snap out of it and realize you're going to have to go look for yourself. Well, that's what the problem is. We got a ton of people that just show up in comments and show up in chats and just say, well, show me your map, show me your model. And if you say you don't have it, then they're dismayed, because they're like, well, I already have something that works. Well, then that's fine. Then you can believe the lie that you were taught and enjoy that. Some of us can't stand that. Some of us demand to know the truth, and we know we're not going to get it from anybody but ourselves and like-minded people who are willing to go out and test. And
if you were to take the dead center of each of those lines, what would direct east and west be? So like the dead center of the red line, what would east and west be there?
So you mean like from right here?
Right here, like what would east and west look like?
90 degrees would be 90 degrees east is here. See, because it really angles up with this, this line here. And I always get confused. What is this? This is latitude?
Right.
So, that would be, but it's the same thing on the flat earth, John. Like if you got down real close to where this line is, that every single direction. So if you start here and went 90, then it would be here. And then if you started here, then it's going to keep going along this line. See, it's going to always stay, with that line. And that would be 90 east the whole time if I kept doing little lines. But if you're talking about a heading, meaning you start heading that direction, then your 90 east veers off that line. So it's kind of, this is what tells me that they took the flat earth and applied it to a globe. Because the flat earth, it's easier to describe the way it works when you think of the north being at the center, and the fact that every step you take, your compass has to readjust to where the north is, which is going to kick. Let's say we're going east like this. So as we take one step, the north kind of turns a little bit, which is going to kick our east up towards the north, just a little hair. So every step you take, you're kicking that east up north, and that allows you to stay on that white line. But if you're talking about a heading, then you're just talking about pointing in that east direction and following that path. And in which case you would follow the red line, not staying upon the white line.
And technically, if you headed on a perfect latitude east path, you shouldn't have to adjust much. If the Earth was a sphere, you really wouldn't. It would be more or less a perfectly straight line describing a great circle that went clear to the other side of the Earth. So
the only great circle is the equator, right? I mean, the only great circle going east-west is the equator. Every line going north-south is a great circle. Those are all great circles going north-south. So when you're talking about north-south, that's why we're only talking east-west here. North-south will never change. If they will always be on this line. Directly north will always be, directly north will always be on this line. And directly south will always be on that line. The problem is east-west, unless you're on the equator. The equator, east-west, is going to be exactly on that line. But as soon as you get off here, that's when they veer. Because to stay on this line, you would be heading north. Whereas to go east, your line's going to drop down, because these aren't great circles. There's a name for them, but I forgot what it's called. It's like a semicircle. I don't know what it's called. There's a name that they call these lines, because they're not great circles. So it's just, if somebody would think that if you were here and you went east, that you would just magically go around the globe. Well, you would, as long as you're adjusting to north each step you take, because then you're going to kick east up to the north, and you're going to keep
right. Yeah. Either way, you'd have to make those sort of adjustments, especially far from the equator,
right,
in either model. Yeah.
And you would never really notice it if you were close to the equator, which is why somebody here who sees the sunrise in the east on the equinox, of course, it would just look exactly like they're heading to the east. But even somebody who's way up here, who's looking at the sunrise on the equinox, wouldn't notice, because when you get down and get real down here, well, east is going to look this way. So to them, it is looking towards the east. But really, when you look at the heading, it's going to be a line that drastically cuts all the way down and hits the equator at the down here. So that's how they've gotten away with the whole idea of the equinox and the sun rising at 90 degrees for everybody, because we all thought 90 degrees is, anywhere you're at, you just draw a cross, and 90 degrees is this way. Well, that's true, but remember how far away the sun is to be rising above the horizon. That's really the direction that you're looking.
The hyperbolic paraboloid shape of the sun analemma is not just a path over a year time span. But that same motion is found in the sun's 24-hour cycle. This drift pattern becomes obvious when you track the sun with high-end trackers like Los Mondi trackers, and just track the azimuth of the sun and do not use the correction adjustments of the tracker so that it runs on its nominal speed of 15 degrees an hour. The drift pattern is also equal and opposite on both sides of the equator, which means that this small 39.8 mile diameter sun is moving across the sky at various observed speeds north and south of the equator. After 2 years of research and modeling, we were stuck and couldn't make it work to model the sun or any object accurately. We started from scratch again. After looking at photos of crepuscular rays of the sun, which all flat earthers have seen a million times, we came to a revelation many, if not all, flatheads have overlooked. When you look at crepuscular rays piercing through clouds over a lake or plain, for example, the angles of the rays end up at the actual light source, which is just above the clouds in most cases. But we know the sun is not right above the clouds. We started wondering what someone would see looking back from the other side, and if he or she would see the same thing. Imagine a scenario where you see these rays over a lake. Those rays are lighting up a spot on the water. Now put another observer right across the lake looking back at you. Can he see those rays in that lit up spot on the water like in this animation? Let's take that one step further and give the primary observer seeing the rays a long pole with a mirror attached at the end. If he were to reflect that ray hitting the water to the observer on the other side, would he then see a reflection of the sun in that mirror? Keep in mind the distance apart here is only 40 kilometers, and where the sun should be for the observer on the other side. To make these light angles in 3D software, you will need, like we used here, a local light source. But in reality, when you move to the other side of the lake and turn around to look back, you will have the sun at your back. Therefore making it impossible to see the rays in the first scenario or the reflection of the sun in the mirror. We have therefore come to the logical conclusion that those rays are personal for any observer, as someone looking back cannot see the same thing because of his position towards the sun. Now, if those rays are personal and cannot be seen by anyone else but the observer himself, that indicates that the sun is a personal or local objective projection. This can be verified by anyone by doing the opposite side crepuscular rays experiment, like in this animation, and see that someone looking back at someone seeing those rays cannot and will not see the same thing. A rainbow acts the same way as the sun, being that you can only see it at a specific angle, and you cannot walk around a rainbow as it will always move away from you. And you cannot see the opposite side of a rainbow. A rainbow is a source projection, and its source is the sun. Therefore, if the sun is also a source projection of an unknown source, we can start modeling the path of the sun for each observer on Earth. We did this by taking just one longitude, that being the 0 UTC meridian on Earth. And inputted the data from observations for azimuth and declination of the sun and traced the sun object for that location for a year for each 10th latitude north and south of the equator, and just let the data run its course for a year. But the model became so heavy with data and tiny hair-thin tracer lines that even with a super machine, we couldn't render the result. After some trial and error, we finally managed to get a clear view on the end result. And even with our sun being an equal distance to the observer, the shape and layout ended up in a torus field around the Earth. We still have to figure out how to do proper 3D vectoring to get all the observed speeds and changes in the motion of the sun, creating a more true shape. But it became very clear to us that based on Ken Wheeler's research into magnetic holography, that the sun we see is projected into the electromagnetic field in the sky. The objective sun follows the magnetic field lines that are unique for each location on Earth. So the real sun is a source coming from outside of the so-called firmament, which probably uses light polarization that is projected into the magnetic field and rendered through the atmosphere. It is no coincidence that all sun arcs combined create this torus-like field, and this is version 1.0. As soon as we find out how to use equal distance 3D vectoring and a formula on the angles in the data sheets from observations, we can then get a true shape in second-by-second motion in the field lines. This torus field is by no means a stationary field, as the sun moves north and south during the year. We animated this in what we call the cosmic breath of flat Earth, and this shows that by simply increasing the current in the field from the North Pole, you then push the field south, and by lowering the current, it flows back north again. It can also be pushed back and forth by an outside magnetic field from beyond the Antarctic, 90 degrees south latitude. The southern magnetic anomaly is also a moving anomaly, and who knows what more lies beyond the southern latitudes, all of which have influence on the field. From a creation standpoint, it must have a function as well. If we animate all sun positions over a year, the animation gives the impression of a wave going around the field like an outside source pushing and pulling on the field and projecting its image, that being the sun or moon, in it. We do not know yet what, where, and how this outside source is mechanically working, so to speak, but from an engineer's perspective, everything that works like a machine or clock must have a basic principle and laws of physics to discover its nature. We just have to figure out where to go from here and what experiments can be derived to either build on this or modify the basic concept. With this concept, we can boldly say we have created a working flat Earth model that can be held up to scrutiny, evaluation, testing, and experimenting to either verify or debunk certain aspects of this model. It is therefore with great honor and humility that we present this first and only working flat Earth model with an actual base in geometry, science, and observations. In the coming weeks, we will be releasing ground views of this model to show that current sun angles are dead on correct.